I am Vineet Kumar Sinha from ABS Engineering College, Ghaziabad. In this video lecture series, we are discussing the subject Materials Engineering, and we are discussing Unit 2 phase diagrams. And in today's video, I'm going to cover the topic binary eutectic systems. So as per syllabus, we'll be covering the topic binary eutectic systems, taking an example of lead tin system, and also the microstructure development in eutectic alloys. So we have already discussed in our last lecture the binary systems, having the isomorphous systems, and just an introduction of eutectic system. So going it further, having the lead tin system, let us go it in detail. So three single phase regions are found on the diagram, alpha, beta, and liquid. Just for a recall, we discussed as eutectic system where a liquid phase is directly, suppose we can see over here, a liquid phase is at a point, this liquid phase, complete liquid phase will be converted into two different solid phase. Phase transformation would take place and there would be an invariant reaction involved. Invariant reaction means at any instance, at any point for a particular composition, all three different phases would be present. So here this liquid L would be converting into alpha plus beta, two different solid phases at 61.9 10% composition, that is called CE, and at a particular temperature that is 183 degrees Celsius. This is for particular lead tin system which we are considering. So eutectic reaction means one liquid phase is converted into two different solid phases. So here three single phase regions are found on the diagram, alpha, beta, and liquid. Alpha and beta, now two separate solid phases would be present, and also liquid. Beta phase is a solid solution rich in tin or SN, having 232 degrees Celsius melting temperature. This is a typical, if we see, this is a typical phase diagram for binary eutectic system. So we need to have the interpretation of this, interpretation of this eutectic system, that is lead tin system. Here, beta phase is a solid solution. Beta phase where this is the beta phase. This is marked beta phase. So beta phase is the single phase, single solid, complete solid solubility of lead in tin, because here almost 100% tin is there and lead would be very less. 100% tin and lead would be very less. So the solubility of lead in tin is beta. Solid solution rich in tin or SN, having 232 degree. 100% tin is having 232 degrees Celsius is the melting point. Here it is marked. Alpha phase solid solution of lead or 327 degrees centigrade. This is alpha phase. This complete region is alpha phase, where entirely alpha would be present, entire single solid would be present, and there would be 100% solubility of tin in lead, because here lead is 100% and tin would be 0%. So at this 100 and 0 combination, the melting point of lead is 327 degrees Celsius. This point is A. The eutectic invariant point is located at 61.9 weight% tin and 183 degrees Celsius. So this 61.9 weight% tin is here, this point, and temperature 183 degrees Celsius, we can mark over here. So 183 degrees Celsius, this point we can locate. This is the eutectic point or invariant point. At this point, what we discussed just now, this liquid will transform into alpha plus beta. So basic, since we are discussing the eutectic system, so this eutectic point or invariant point is of prime importance. Let us see one by one. The solubility in each of these solid phases is limited in that at any temperature below line BEG, only a limited concentration of silver will dissolve in copper for the alpha phase, and similarly for copper in silver for the beta phase. What we saw, line BEG, this line BEG, below this BEG, below this two separate phases would be present, solid alpha plus beta, and limited solubility would be there. The solubility limit for the alpha phase corresponds to the boundary line labeled CBA. This CBA this C, this B point and A. Inside this, 100% solubility was there, so alpha phase would be present. And similarly, beyond this H, G and F, beyond this H, G, F region, only single phase beta would be present. Complete solubility of one into another. The solubility limit for the alpha phase corresponds to the boundary line labeled CBA. It increases with temperature to a maximum 18.33 weight% 10 at 183 degree at point B, and decreases back to 0 at the melting temperature of point pure lead, that is point A. Here we can see the solid solubility line is maximum, means at this maximum 18% or roughly 18 to 19% of tin would get dissolved in lead at 183 degrees Celsius. Above this temperature, again, the solubility will go down and subsequently it will reduce to 0. Means no tin would be, at this temperature 327 degrees Celsius, no tin would be dissolved in solid lead, and 100% lead would be melting. At temperature below 183, the solid solubility limit line separating the alpha and alpha plus beta phases is termed a solvus line. So this is the alpha C point, the B point and C point. This line is called solvus. So below 183 degrees Celsius, this is the line. At various composition and at various temperature, this alpha would convert into alpha plus beta, two separate solid phases. The boundary AB between the alpha and alpha plus L fields is the solidus line that we have discussed. Similarly, for the beta phase, both solvus and solidus lines also exist, HG and GF. So HG and GF, these two lines are for beta phases. The maximum solubility of tin in the beta phase point G is 2.2 weight% at 183 degrees Celsius. So this is 2.2 weight% of lead. So the tin would be 97.8%. So here it is mentioned 97.8% tin means 2.2% lead. So 2.lead% is the maximum solubility of 2.2 weight% of lead is the maximum solubility of in tin, 97.8% at 183 degrees Celsius. Beyond that temperature, it will again reduce. The solubility will go down. The horizontal line BEG, which is parallel to the composition axis and extends between these maximum solubility, may also be considered a solidus line. So this line is also a solidus line. This line BG is also solidus line. This is solidus line, and this is solidus line. This is liquidus, It's mentioned this is liquidus and this is solvus, and again this is solvus. It represents the lowest temperature at which a liquid phase may exist for any tin-lead alloy that is at equilibrium. So this solidus line is also representing this line BEG is an important line in this system, eutectic system. Below this, no liquid phase would be present. Below this line, at any composition, no liquid phase would be present. Only solid phases, either alpha or beta, a combination of alpha beta would be obtained. Point E is called an invariant point. Here in this figure, we can see point E is the invariant point. And invariant reaction, we can write liquid having composition Ce is when we heat or cool, then it will get converted at this point only alpha C alpha E plus beta C beta E. Means this at liquid at Ce, liquid at Ce would at this instant will convert into C alpha of 18.3 and C beta 97.8 weight percent mass fraction. L 61.9 weight percent in cooling, alpha would be 18.3 weight percent and beta would be 97.8 weight percent tin. Upon cooling, a liquid phase is transformed into two solid alpha and beta phases at the temperature T. The opposite reaction occurs upon heating. This is called a eutectic reaction. When we cool down from solid liquid to two solids, and when we heat two solids to liquid at the same point, that is E point, what we have seen this at E point simultaneously when we cool a liquid from this region to this crossing this point, then at this point only this alpha plus it will transform into alpha plus beta, and so simultaneously when alpha plus beta of this composition will get heated at this point E, it will simultaneously converting into liquid at any instant instantaneously. This is called eutectic reaction. To determine the fraction of phase at eutectic point in tin lead system, at point E, C alpha, the weight percent of tin is 18.3 weight alpha. The composition of alpha would be 18.3, beta would be 97.8, and Ce would be 61.9. So the mass fraction of alpha, we can calculate mass fraction of alpha. Since alpha is this point, mass fraction of alpha would be opposite arm means GE divided by total BG. है means C beta minus Ce upon C beta minus C alpha. C beta minus Ce upon C beta minus C alpha. And when we calculate this, we will have 45.2% of mass fraction of alpha phase. And beta phase, Ce minus beta phase, how can we calculate? Opposite arm. Opposite arm is this Be. So Be upon Bg. That we can write as Ce minus C alpha upon C beta minus C alpha. This will be equal to W beta. So W beta is same thing. What we have written there. Ce minus C alpha upon C beta minus C alpha, and that comes to 54.8%. So the combination of alpha and beta at point E is 45.2% is alpha and 54.8% is beta. This is how we can calculate from the phase diagram, we can interpret what is the mass fraction of both the phases present and what is the how the phases are changing as per the composition and temperature variation. Development of microstructure in eutectic alloys. How can we interpret them? So first, let us take an example of point C1. This is point C1. This C1 is having composition where it is not going beyond this solvus line and this solidus line. This is cutting only solidus line. So when we cool any of this composition from this 380 or 350 degrees Celsius along this vertical line, dotted line, we can have a liquid, complete liquid phase here where this single phase would be present. Then at this point, both liquid and solid would be present. We can mention this as this, like this, and then complete alpha would be present. It's a single phase alpha would be present, and till the room temperature only alpha would be present. Similarly, if we consider this C2 point having the composition around 15 degrees Celsius, 15% of tin in lead, and we try to cool it from this above 350 degrees Celsius, this D point, if we consider this is having completely liquid solution, having C2 weight percent CN, similarly C2 weight percent CN, then at this E point, we'll have a combination of alpha. Alpha is growing into, is solidifying and in liquid. Then at this point, complete alpha means complete changing into complete whole alpha would be present. And then again, when it goes down below this temperature, then due to limited solid solubility, it will again change into two phases, alpha plus beta. So here the microstructure would be somewhat like alpha plus beta. So how this microstructure gets changed at different temperature gives the properties of the material at that temperature, what we discussed earlier. Similarly, when you consider C3 point, C3 point is what? The eutectic point or the eutectic point is at which composition. So if we go down from this Y point or this H point, at this H point, we consider the 61.9 weight percent tin combination at this 250 or 255 degrees Celsius, this is completely liquid. And when we reach at this eutectic point and just below eutectic point, we have just two alpha plus beta, two types of solid. And the weight percent of this would be alpha would be 18.3% and beta would be 97.8%. And this is in the form of this alternate lamellae, alternate layer of alpha and beta. And this is typical type of alpha plus beta combination. And till room temperature, it would be like this one. Similarly, we consider this point C4. The composition C4 means 40 weight percent tin and 60 weight percent lead. Then starting from point J, here it is completely liquid. Inside this, alpha plus liquid. So alpha starts to precipitate, solidify, and liquid is also there. So in liquid, few chunks of alpha would be there. Then at point L, major portion gets converted to solid and liquid is very less. And at this point, complete would be changed. This alpha would be still be there, and also this lamella will form of this eutectic combination. So this eutectic structure would also be there. Primary alpha would also be there. These are the primary alpha. These are the primary alpha. The chunks what was generated here, these chunks will remain. And till further we cool it down, these chunks will remain. And also this liquid, what was available here, this liquid, will at this point will transform into this lamella or this alternate layer of eutectic structure, primary alpha and beta. So at this, any point in this combination, at this point, at this temperature, three things would be there. A combination of primary alpha and primary beta, and a primary alpha and also eutectic alpha and beta. Three things would be there. And how can we calculate the mass fractions of those? So here this is written W eutectic equals to WL. It is equal to P upon P plus Q as per the lever rule. We can find out all these things, all these equations. And mass fraction of beta would be equal to P at this point C4 dash. If we calculate mass fraction of beta would be opposite arm, this P divided by P plus Q plus R. Similarly, it is written here P upon P plus Q plus R equals to C4 dash minus 18.3 divided by 97.8 divided minus 18.3. So it will be this figure. And W alpha, W alpha would be opposite arm, means from here say this Q plus R upon P plus Q plus R. Similarly for alpha dash, this eutectic alpha, it is Q opposite arm, this opposite arm divided by P plus Q. And for eutectoid equals to L is equals to P upon P plus Q. Similarly, we can calculate these values. So this is as of now. In this video, we'll discuss the next topics in subsequent videos. Thank you.